Max Planck's journey into the laws of nature was deeply rooted in his quest to solve one of the most perplexing issues of his time: the ultraviolet catastrophe. The issue arose from the study of blackbody radiation, a phenomenon where a perfect absorber and emitter of radiation, known as a blackbody, absorbs all wavelengths of light and re-emits them in a continuous spectrum. Classical physics, particularly the laws of thermodynamics and electromagnetism, had provided an understanding of how matter and radiation interacted, but these laws were unable to explain the behavior of radiation at short wavelengths, specifically in the ultraviolet range. Theoretical models, based on the classical assumptions of continuous energy, predicted that as the wavelength of radiation decreased, the intensity of radiation emitted by the blackbody should increase without bound. This paradox, known as the ultraviolet catastrophe, was not just a theoretical issue, it directly contradicted experimental results, which showed that radiation intensity did not increase infinitely at short wavelengths, but rather tapered off. For scientists at the time, this presented a deep mystery. Why did the predictions of classical physics break down at these extreme wavelengths? Why did they fail to match what experiments showed? The search for an answer to this question would lead Planck to a groundbreaking realization, forever changing the course of physics. At the turn of the 20th century, the study of blackbody radiation was at the forefront of scientific inquiry. Researchers, including the German physicist Wilhelm Wien, had attempted to address this issue. Wien's law, which described the distribution of radiation at different wavelengths, was useful at shorter wavelengths, but failed to explain what happened at longer wavelengths. Then came Rayleigh's law, which described the radiation at longer wavelengths, but, once again, broke down in the ultraviolet range. In an effort to resolve this paradox, Planck took a different approach. He began by trying to understand the relationship between temperature, radiation, and energy. Planck's goal was to find a formula that would match the observed radiation curve across all wavelengths. To do this, he first focused on the idea that the energy of radiation in a cavity could be quantized. However, this was not an immediately obvious or popular solution. Classical physics viewed energy as a continuous quantity that could take on any value within a given range. Planck, on the other hand, introduced a new hypothesis: energy was not continuous, but rather could only exist in discrete amounts, or quanta. Planck's breakthrough came from considering the behavior of radiation in a cavity containing standing waves. He assumed that energy was not continuously distributed among the waves, but was divided into discrete units. He postulated that each standing wave could only have certain energy levels, with each level being a multiple of a fundamental unit of energy. This quantization of energy seemed a radical departure from classical ideas, which had always assumed that energy could be freely exchanged in any amount. To describe the energy of these quanta, Planck introduced a constant later known as Planck's constant, denoted by hhg. This constant would play a pivotal role in all of quantum theory, linking the frequency of radiation to its energy. At the time, Planck did not fully grasp the revolutionary implications of his discovery. He initially conceived the idea of quantization not as a fundamental principle of nature, but rather as a mathematical trick to match the experimental data. His main goal was to derive a formula for blackbody radiation that would accurately explain the observed spectrum, and this approach worked. Planck's radiation law, which he formulated in 1900, was able to perfectly match the experimental data for blackbody radiation at all wavelengths, including the ultraviolet range. The formula was a triumph of mathematical elegance, and it provided the resolution to the ultraviolet catastrophe that had plagued scientists for decades. Planck's formula was groundbreaking, but his concept of energy quantization remained a controversial and perplexing idea. The physics community was deeply rooted in classical mechanics, and the concept of discrete energy levels seemed to fly in the face of the continuous nature of classical theories. However, Planck's work was undeniably successful in addressing the specific problem at hand, and it opened the door to new ways of thinking about the physical world. Over the next several years, Planck's work would be extended and expanded by others, including Albert Einstein, who would use Planck's quantization of energy to explain the photoelectric effect, and Niels Bohr, who would apply quantization to the behavior of electrons in atoms. Although Planck was not the first to suggest the idea of quantization, his approach and mathematical framework were the most successful in explaining the data. His insights would eventually lead to the development of quantum mechanics, a theory that would revolutionize physics and our understanding of the universe. However, Planck himself was initially hesitant to embrace the full implications of his work. He continued to believe that his quantization method was a temporary solution, a mathematical tool to help solve a specific problem. He did not initially envision it as a fundamental principle of the universe. Planck's work was a significant departure from the classical worldview, but it was not immediately recognized as a step towards a new understanding of the physical world. At the time, quantum mechanics was not yet a fully developed theory, and the idea of quantization seemed like an isolated, almost artificial concept. Planck himself was reluctant to fully accept the implications of his work and resisted the idea that energy quantization was a fundamental feature of nature. Despite this, his radiation law provided a crucial first step in the development of quantum theory, and the constant he introduced became one of the most important quantities in physics. Planck's search for the laws behind the laws of nature was not just an academic pursuit, it was a journey into the unknown. He was attempting to uncover the hidden truths of the universe, and in doing so, he took a bold step that would eventually reshape the entire field of physics. His work was not just about solving a specific problem in blackbody radiation, it was about challenging the very foundations of how we understand the world. In this sense, Planck's search was not just a scientific endeavor, but a philosophical one as well. It forced scientists to confront the limitations of classical physics and to consider the possibility that the universe operates according to laws that are far stranger and more complex than previously imagined. Planck's contributions to physics were profound, but his journey was not without its challenges. He faced resistance from many in the scientific community, particularly from those who held fast to classical ideas. Nonetheless, his insights paved the way for a new era in physics, and his work became the cornerstone of the quantum revolution. Through his relentless search for understanding, Max Planck unlocked a new way of thinking about the world, a way that continues to shape the future of science. Max Planck's work, especially his resolution of the ultraviolet catastrophe, laid the foundation for quantum mechanics and ushered in a new era of physics. His initial formulation of the energy quantization concept was born out of his desire to understand the relationship between temperature, radiation, and energy. However, it would take more than just solving the blackbody radiation problem for Planck's ideas to gain full recognition in the scientific community. Although his theory of quantization was the first crucial step towards quantum mechanics, it was far from the last. Planck's law, derived from this hypothesis, became central to the development of modern physics, but understanding its significance required a much deeper reevaluation of what the universe itself could be like. Following Planck's initial work, the next major step in quantum theory came from Albert Einstein. In 1905, Einstein used Planck's quantization of energy to explain the photoelectric effect, another long-standing mystery in physics. The photoelectric effect involved shining light onto a metal surface and observing the emission of electrons. Classical theory failed to explain why light of a certain frequency could cause electron emission, while lower frequency light, even at higher intensities, could not. Einstein proposed that light itself is quantized, consisting of discrete packets of energy called photons. This idea not only supported Planck's notion of quantization, but also led to Einstein's Nobel Prize in Physics in 1921. Einstein's work helped solidify Planck's idea that the quantization of energy was not just a mathematical trick, but a fundamental characteristic of the physical world. However, it wasn't until Niels Bohr's work on the atom that the full implications of Planck's ideas became clearer. Bohr took Planck's quantization and applied it to the behavior of electrons in atoms, demonstrating that electrons could only occupy certain discrete energy levels. This model was the precursor to the modern quantum mechanical model of the atom and was crucial in explaining phenomena like atomic spectra. Bohr's work, influenced by Planck's ideas, was another essential step in the development of quantum mechanics. Planck's contributions extended far beyond the introduction of energy quanta. He also made significant strides in understanding thermodynamics, particularly in the context of statistical mechanics. Statistical mechanics seeks to understand the behavior of large systems of particles by relating macroscopic properties, like temperature and pressure, to microscopic properties, like particle interactions. Planck was instrumental in shaping the statistical foundations of thermodynamics, and his work paved the way for the later development of the field by scientists like Ludwig Boltzmann and James Clerk Maxwell. As the 20th century progressed, the development of quantum theory accelerated, with Planck's work serving as the cornerstone for virtually all of it. Planck's constant, became one of the most important physical constants, central not only to quantum theory, but to fields ranging from atomic physics to cosmology. The Planck constant plays a critical role in the famous equation E equals hc.f, where E is the energy of a photon and F is its frequency. This simple equation encapsulates the very essence of quantum mechanics, providing a bridge between the world of the very small atoms, photons, and electrons, and the macroscopic world of classical physics. Despite the profound impact of his work, Planck remained largely modest about his role in the development of quantum theory. He viewed his quantization hypothesis as an isolated solution to a specific problem rather than as a door opening to a whole new way of understanding the universe. He never fully embraced the radical implications of his work, as he struggled with the philosophical implications of a universe governed by uncertainty and probability, as later theorized by Werner Heisenberg and others. Planck's own philosophical stance on quantum mechanics was rooted in a desire for physical realism, the belief that the world was governed by definite laws, even if we could not always measure them directly. He was wary of the more abstract ideas of quantum mechanics, especially Heisenberg's uncertainty principle, which suggested that the position and velocity of particles could not both be precisely known at the same time. Yet, despite his reservations about some of the more far-reaching conclusions of quantum mechanics, Planck remained one of its most vocal proponents. His intellectual integrity and curiosity pushed him to accept the necessity of the new theory, even if it conflicted with his deeply held beliefs about the nature of reality. In the end, Planck's search for the laws behind the laws of nature became not just about solving one problem in black-body radiation, but about unlocking the secrets of the universe itself. His work is considered one of the defining moments of modern physics. Planck's influence extended beyond the realm of theoretical physics. His insights into the nature of science and scientific progress were profound. He believed that scientific advances were often born out of struggle, and that the process of discovering new laws was often filled with uncertainty and resistance. In many ways, Planck's own experience reflected this view. His revolutionary ideas were initially met with skepticism, and it took years for his work to be fully appreciated. Despite this, he remained steadfast in his commitment to the search for truth, knowing that the path to discovery was rarely straightforward. Max Planck's life and work offer a powerful reminder of the importance of intellectual curiosity and perseverance. He understood that science is not just about solving immediate problems, but about searching for deeper truths that transcend the problems themselves. In his search for the laws behind the laws of nature, Planck touched on one of the most fundamental aspects of the human experience, the desire to understand the universe at its deepest level. His contributions laid the foundation for quantum mechanics and continue to shape the way we understand the world. His legacy lives on in the work of countless scientists who have built upon the insights he first uncovered, reminding us that the search for knowledge is an ongoing journey that knows no bounds. Max Planck's work, which laid the foundation for quantum theory, was revolutionary not just for its contribution to physics but also for the profound philosophical questions it raised about the nature of reality. Planck's contributions began with his solution to the ultraviolet catastrophe, a dilemma in classical physics that sought to explain the nature of radiation emitted by black bodies. Blackbody radiation was a significant area of study in the late 19th century. It refers to the way objects absorb and emit radiation depending on their temperature. Classical physics predicted that a black body would emit an infinite amount of energy at short wavelengths, something known as the ultraviolet catastrophe. This prediction did not match the observed experimental data. At that time, the laws of classical physics, particularly those related to electromagnetism and thermodynamics, were widely accepted and had successfully explained many physical phenomena. However, when it came to explaining the behavior of radiation at extremely short wavelengths, classical theory was insufficient. Planck was deeply aware of this discrepancy and sought to resolve it by studying blackbody radiation in a new way. Planck's breakthrough came when he introduced the concept that energy could only be emitted or absorbed in discrete units, or quanta. This was a radical departure from the prevailing belief in continuous energy and set the stage for the development of quantum mechanics. Planck's proposal was based on the mathematical necessity of introducing quantization in order to match experimental observations of blackbody radiation. His mathematical derivation led him to introduce a new constant now known as Planck's constant, denoted as h, which played a pivotal role in linking the energy of radiation to the frequency of the radiation wave. This constant became one of the most important fundamental constants in all of physics. Initially, Planck viewed this idea as a mathematical trick to solve a specific problem, not as a reflection of a deeper truth about the nature of the universe. It was a mathematical device used to reconcile the discrepancies between theory and experiment, and he did not yet fully understand the profound implications of his discovery. Planck's work marked a pivotal moment in physics. By quantizing energy, he provided a resolution to the ultraviolet catastrophe, but he did not initially recognize the full extent of his insight. His quantization of energy was a small piece of a much larger puzzle, one that would eventually unravel and revolutionize the entire field of physics. Although Planck had offered a solution to the radiation problem, his theory did not have immediate acceptance in the scientific community. It was a very radical departure from classical physics, which viewed energy as a continuous quantity. As a result, Planck's ideas faced resistance from many physicists who were deeply committed to classical mechanics and its assumptions. Planck's radiation law, derived from the quantization concept, was a success in that it accurately described the spectrum of radiation emitted by black bodies, but it seemed, at first, to be an isolated solution for a specific problem. The significance of Planck's work became clear in the years that followed, as it laid the foundation for the entire field of quantum mechanics. After Planck's initial insight, other physicists, such as Albert Einstein, Niels Bohr, and Werner Heisenberg, extended and built upon his work. In 1905, Einstein used Planck's idea of quantized energy to explain the photoelectric effect. The photoelectric effect involves the emission of electrons from a metal surface when light shines upon it. Classical physics predicted that the intensity of light would determine the number of electrons emitted, but experiments showed that only light of a certain frequency could cause electron emission, no matter how intense the light. Einstein proposed that light itself was quantized, existing as discrete packets of energy called photons. This was a crucial extension of Planck's work, and served to solidify the idea of quantization as a fundamental property of nature. Einstein's use of Planck's idea in explaining the photoelectric effect helped to demonstrate that the quantization of energy was not just a mathematical construct to fit the data, but a reflection of the true nature of light and energy. His explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921, and it helped to establish the idea of photons, which became a cornerstone of quantum theory. Einstein's success was, in many ways, a direct result of the framework that Planck had developed. In this sense, Planck's contributions were not just about solving the ultraviolet catastrophe, but about fundamentally altering our understanding of the world at the most basic level. His insights provided a theoretical basis for much of the revolutionary work that followed, shaping the course of modern physics. Max Planck's discovery of energy quantization and his formulation of Planck's radiation law were also foundational for Niels Bohr's work on atomic structure. In 1913, Bohr extended Planck's ideas to the structure of atoms, suggesting that electrons in an atom could only occupy specific quantized energy levels. The Bohr model of the atom, which explained the discrete lines observed in atomic spectra, was another direct consequence of Planck's quantization theory. Bohr's model, along with Planck's radiation law, helped to solidify the idea that not only energy but also matter behaved in a quantized fashion. Bohr's work paved the way for the development of quantum mechanics, a theory that would transform our understanding of the microscopic world. Planck's work was the starting point for all of this, a crucial first step that would eventually lead to a complete overhaul of classical physics. The radical nature of Planck's discoveries, however, was not lost on him. Planck himself was initially reluctant to embrace the full implications of his work. He struggled with the philosophical implications of quantization, which seemed to contradict the classical idea of a deterministic and continuous universe. Planck believed in the possibility of a fully deterministic universe governed by strict, knowable laws. The uncertainty and probabilistic nature of quantum mechanics, which would later be developed by Werner Heisenberg and others, was something that Planck was not comfortable with. Nonetheless, despite his reservations, Planck recognized that his work had opened a new door to understanding the universe. He continued to support quantum theory throughout his life, although he remained wary of its more abstract and uncertain aspects. As quantum theory developed throughout the 20th century, Planck's work remained central to the development of modern physics. His insights were integral to the formulation of both quantum mechanics and statistical mechanics, fields that continue to shape much of today's technological advancements. The contributions of scientists like Einstein, Bohr, Heisenberg, and Schrödinger all built upon the groundwork laid by Planck. Quantum mechanics, with its probabilistic nature and strange implications, remains one of the most successful and accurate theories ever developed. Planck's initial insight into the quantization of energy, though initially met with skepticism, has since been recognized as one of the most important contributions to science. Planck's legacy in the world of physics is vast and enduring. His work laid the foundation for virtually every aspect of modern physics, from the understanding of atomic and subatomic particles to the development of technologies such as semiconductors, lasers, and quantum computers. Beyond his scientific contributions, Planck's journey serves as a reminder of the importance of intellectual perseverance in the face of uncertainty. Planck's search for the laws behind the laws of nature was not just a scientific endeavor, it was a quest to uncover the deepest truths about the universe. His work continues to inspire new generations of physicists and serves as a testament to the power of curiosity and the pursuit of knowledge in the face of the unknown. Through Planck's work, the very fabric of reality was revealed to be far more mysterious and complex than previously imagined. His discoveries marked the beginning of a new era in science, one that would ultimately redefine our understanding of the universe and our place within it. Planck's legacy continues to influence not just theoretical physics but also the way we think about the fundamental nature of existence itself. His contributions to science and to our understanding of the cosmos remain as relevant today as they were when he first formulated his revolutionary ideas. Max Planck's journey in quantum physics was not just about solving specific scientific problems. It was about unlocking the mysteries of the universe and challenging the very fabric of classical physics. His search for the underlying laws of nature began with the ultraviolet catastrophe, a problem that arose from the behavior of blackbody radiation. This issue puzzled scientists for years because classical physics failed to explain why the radiation emitted by hot objects at higher frequencies, especially in the ultraviolet range, did not align with experimental observations. In simple terms, classical physics predicted that a black body, a theoretical object that absorbs and emits radiation perfectly, would emit an infinite amount of energy at short wavelengths, a result that contradicted the reality observed in experiments. This failure of classical physics to explain blackbody radiation became one of the key motivators behind Planck's groundbreaking work. Planck's approach to resolving the ultraviolet catastrophe was a radical departure from traditional physics. Instead of assuming energy to be a continuous quantity, as classical theory did, Planck hypothesized that energy was quantized. He proposed that energy could only be absorbed or emitted in discrete amounts, or quanta, which was a concept entirely foreign to classical physics. The introduction of this idea was not just a mathematical trick, it was an entirely new way of thinking about the very nature of energy. This shift from a continuous to a discrete model laid the groundwork for the quantum revolution that would transform the entire scientific landscape. At first, Planck did not fully appreciate the magnitude of his discovery. His quantization of energy was a mathematical necessity, a means to resolve the discrepancies between theory and experiment in the context of blackbody radiation. Planck's radiation law, which described the relationship between temperature and radiation emitted by a black body, provided a perfect fit with experimental data, something classical theory had failed to do. Planck introduced a constant, which came to be known as Planck's constant, denoted as h, to describe the relationship between the energy of radiation and its frequency. The constant became one of the most fundamental quantities in physics, and it played a crucial role in the emerging field of quantum mechanics. Although Planck's radiation law was successful in explaining the observed behavior of blackbody radiation, his idea of energy quantization faced resistance from the scientific community. At the time, the prevailing worldview was still dominated by classical physics, and many physicists found it difficult to accept the idea that energy was not continuous. Planck himself was initially reluctant to embrace the full implications of his work. He viewed quantization as a temporary solution, a mathematical trick to fit the data, rather than a fundamental principle that could potentially describe the nature of the universe. However, as more experiments were conducted and as the limitations of classical physics became increasingly apparent, Planck's theory gained acceptance, and the quantum revolution began to unfold. While Planck's work had already set the stage for the development of quantum mechanics, it was Albert Einstein who took Planck's ideas and applied them to the photoelectric effect in 1905. The photoelectric effect, where light striking a metal surface causes the emission of electrons, posed another challenge to classical physics. Classical theory predicted that the intensity of light, rather than its frequency, should determine whether electrons are emitted. However, experimental results showed that only light of a certain frequency could cause electron emission, regardless of its intensity. Einstein, building on Planck's work, proposed that light itself was quantized and consisted of discrete packets of energy, or photons. This was the first direct extension of Planck's ideas into the realm of light, and it helped establish the concept of photons as fundamental particles of light. Einstein's explanation of the photoelectric effect not only validated Planck's concept of quantization but also demonstrated the applicability of quantum ideas to phenomena beyond blackbody radiation. Einstein's work was crucial in furthering the acceptance of quantum theory and earned him the Nobel Prize in Physics in 1921. It also showed that quantum theory was not just a theoretical construct to solve specific problems, but was instead a fundamental way to understand the nature of light and energy. The significance of Planck's work deepened further with Niels Bohr's model of the atom. In 1913, Bohr applied the concept of quantization to the structure of atoms, a problem that had puzzled scientists for years. Bohr proposed that electrons in atoms could only occupy specific quantized energy levels. This was a direct consequence of Planck's idea that energy could only exist in discrete amounts. The Bohr model helped to explain the discrete spectral lines observed in atomic spectra and was an important step towards the development of quantum mechanics. Bohr's work, along with the contributions of scientists like Heisenberg and Schrödinger, would eventually lead to the establishment of quantum mechanics as the dominant framework for understanding the microscopic world. Planck's work not only contributed to quantum mechanics, but also helped to bridge the gap between classical thermodynamics and the emerging field of statistical mechanics. Statistical mechanics seeks to explain the macroscopic properties of systems, like temperature and pressure, by considering the microscopic behavior of particles. Planck's work on the quantization of energy played a pivotal role in developing statistical mechanics, as it helped to explain how the microscopic behavior of atoms and molecules could give rise to the thermodynamic properties of matter. Planck's contributions to thermodynamics helped establish him as one of the most important figures in modern physics, as he provided the theoretical foundation for much of the work that followed. While Planck's contributions to quantum mechanics were immense, his personal philosophical views about the nature of the universe were not always in alignment with the full implications of his discoveries. Planck was initially deeply uncomfortable with the probabilistic and indeterministic nature of quantum mechanics. As quantum theory developed, it became clear that the behavior of particles at the quantum level was fundamentally unpredictable. Werner Heisenberg's uncertainty principle, for example, suggested that the position and momentum of particles could not both be precisely measured at the same time. This was a far cry from the deterministic worldview that had dominated classical physics. Planck, however, continued to support quantum theory despite his reservations, because he recognized that the theory provided the best explanation for the experimental data. As the quantum revolution progressed, Planck's role as a pioneer became more evident. His work provided the foundation for much of the quantum mechanics that followed, and his constant became a key quantity in the development of the theory. Quantum mechanics, as formulated by Bohr, Heisenberg, Schrödinger, and others, became one of the most successful and accurate theories in the history of science. It led to numerous technological advancements, including semiconductors, lasers, and quantum computers, and transformed our understanding of the microscopic world. Max Planck's search for the laws behind the laws of nature was not just about solving individual problems in physics. It was a quest to uncover the fundamental principles that govern the universe. His work, though initially met with skepticism, eventually became the cornerstone of quantum mechanics, and his legacy continues to shape the field today. Planck's search for knowledge was an intellectual journey that transformed physics and continues to inspire scientists and thinkers in the 21st century. His contributions to the understanding of the universe were groundbreaking, and they remain a testament to the power of curiosity and the pursuit of truth in science. Planck's work set the stage for the quantum revolution, a revolution that continues to unfold as we explore the mysteries of the universe at its most fundamental level. Through his efforts, the universe was revealed to be far more complex, strange, and beautiful than we had ever imagined. Max Planck's search for the laws behind the laws of nature took him into uncharted territory where the very foundations of physics were shaken. His work, which is most famously tied to the development of quantum theory, originated from his attempt to resolve a critical problem that plagued classical physics at the time: the ultraviolet catastrophe. This was a paradox that arose when classical physics was used to predict the radiation emitted by a black body, a theoretical object that absorbs and emits all radiation perfectly. According to the predictions of classical physics, a black body would emit an infinite amount of radiation at shorter wavelengths, a result that clearly contradicted experimental data. The ultraviolet catastrophe was not just a theoretical issue but a profound challenge to the classical understanding of the physical world. Planck's insight into the nature of energy provided the key to resolving this paradox. Planck's approach to solving this issue was entirely novel. Instead of continuing to view energy as a continuous quantity, as classical physics had done, Planck proposed that energy should be considered as quantized, discrete, and not continuous. This concept of energy quanta was a radical departure from the way scientists had been thinking. Classical mechanics, which had been remarkably successful in explaining many phenomena, was based on the assumption that energy and matter could vary in any quantity. However, Planck's hypothesis that energy could only be emitted or absorbed in fixed amounts redefined the very nature of energy itself. This bold step, initially made out of a mathematical necessity to match observed experimental data, became the cornerstone of a new era in physics. To describe this quantized energy, Planck introduced a constant, now famously known as Planck's constant, denoted as h. This constant played a crucial role in the relationship between the energy of radiation and its frequency. The mathematical formula that Planck derived, now known as Planck's radiation law, perfectly explained the observed spectrum of blackbody radiation across all wavelengths, resolving the ultraviolet catastrophe. However, Planck himself did not immediately grasp the full philosophical implications of his discovery. At first, he regarded the idea of quantized energy as a temporary solution, merely a tool to fit the experimental data, rather than a fundamental truth about the nature of the universe. His reluctance to fully accept the profound implications of his work would characterize much of his career, as he was initially skeptical about how far quantum theory might go. Despite Planck's reluctance to embrace the broader consequences of his work, his ideas were groundbreaking, and they would set the stage for the later developments of quantum theory. While Planck provided the first hints of the quantum world, it was Albert Einstein who extended these ideas further. In 1905, Einstein used Planck's hypothesis of quantized energy to explain the photoelectric effect, a phenomenon where light striking a metal surface causes the emission of electrons. Classical physics had failed to explain this phenomenon, as it predicted that light of any frequency should be able to knock electrons off the surface if its intensity was high enough. However, experiments showed that only light of a certain frequency could cause electrons to be emitted, regardless of its intensity. Einstein proposed that light itself was quantized, existing as discrete packets of energy, which he called photons. This extension of Planck's ideas helped cement the concept of energy quantization and played a key role in the acceptance of quantum mechanics. Einstein's work on the photoelectric effect was a significant step in the development of quantum mechanics, as it demonstrated that Planck's quantization idea had far-reaching implications beyond blackbody radiation. The idea that light, traditionally thought of as a continuous wave, could be understood as discrete particles, was revolutionary. It helped pave the way for the development of quantum theory, and Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921. This work also laid the foundation for the later discovery that light could exhibit both wave-like and particle-like behavior, an idea that would later be formalized in the wave-particle duality theory. Planck's initial insight which seemed like an isolated solution to a specific problem, had profound implications for how scientists would come to understand the nature of light, energy, and matter. Planck's work was not limited to the realm of blackbody radiation and energy quantization. He also made important contributions to thermodynamics and statistical mechanics, which helped to bridge the gap between classical and quantum physics. Planck's work on the statistical behavior of energy and its distribution in systems of particles helped to extend the laws of thermodynamics into the realm of atomic and subatomic particles. Statistical mechanics, which deals with the behavior of large systems of particles, was significantly advanced by Planck's insights. His work helped to explain how macroscopic thermodynamic properties like temperature and pressure could be derived from the microscopic behavior of individual particles. This was an important step in the development of modern statistical mechanics, and it played a key role in establishing the broader framework within which quantum mechanics would eventually fit. The implications of Planck's discoveries were not immediately realized, and his work met with resistance from the scientific community. Classical physics, which had dominated scientific thought for centuries, was deeply ingrained in the way scientists understood the natural world. Planck's ideas seemed to challenge the very foundations of classical physics, and many physicists were reluctant to accept the radical departure from the familiar, deterministic worldview that Planck's quantization implied. Planck himself, despite his profound contributions, did not immediately embrace the full implications of quantum mechanics. He continued to believe in the possibility of a deterministic universe governed by strict laws, and he viewed quantum mechanics with some degree of skepticism. Planck's philosophical position, which leaned toward realism, the belief that the universe operates according to definite, knowable laws, was at odds with the uncertainty and probabilistic nature of quantum mechanics that later emerged. This reluctance to fully accept the philosophical implications of quantum theory would remain a theme in Planck's career. Despite his reservations, Planck's role in the development of quantum theory cannot be overstated. His work laid the groundwork for all of the subsequent developments in quantum mechanics. The contributions of scientists like Bohr, Heisenberg, and Schrödinger would all build upon Planck's insights into the quantization of energy. In particular, Niels Bohr's model of the atom, which proposed that electrons could only occupy specific, quantized energy levels, was a direct application of Planck's ideas. Bohr's model helped to explain the discrete spectral lines observed in atomic spectra and was a crucial development in the field of atomic physics. Planck's work also influenced the development of quantum mechanics in fields as diverse as solid-state physics, optics, and nuclear physics, demonstrating the far-reaching impact of his contributions. Planck's constant, denoted as h, became one of the most important fundamental constants in physics. It plays a crucial role in linking the energy of a quantum to its frequency, and it underpins much of the mathematics of quantum mechanics. The constant is used in equations that describe a wide range of quantum phenomena, from the behavior of photons in the photoelectric effect to the energy levels of electrons in atoms. Its role in quantum mechanics is so essential that it has become one of the defining constants of modern physics, appearing in nearly every major equation in quantum theory. Planck's work also had a profound impact on our understanding of the microscopic world. Prior to his discoveries, the physical world was understood in terms of classical mechanics, where particles were treated as small, deterministic objects. However, Planck's introduction of quantized energy and the subsequent developments in quantum mechanics showed that particles at the microscopic level behave in ways that are fundamentally probabilistic. This new view of the world led to the development of the concept of wave-particle duality and the understanding that particles such as electrons do not have definite positions and velocities, but instead exist in a cloud of probabilities. Max Planck's work was foundational to the development of modern physics, and it marked the beginning of the quantum revolution. His contributions to the understanding of energy, radiation, and thermodynamics helped to reshape the way scientists understood the universe. Planck's insights paved the way for the breakthroughs that followed in the 20th century, from the theory of relativity to quantum field theory. His search for the laws behind the laws of nature led to a radical shift in our understanding of the physical world, and his legacy continues to shape the direction of scientific research today. Through his work, Planck revealed a universe far more complex and mysterious than anyone had imagined, opening the door to a new era in science and technology. Max Planck's contributions to science are some of the most pivotal in the history of modern physics, yet his journey to his groundbreaking insights was filled with challenges and intellectual conflicts. The keynotes of his work, which would eventually shape quantum mechanics, were not born from a simple, linear path. Rather, they arose as responses to problems in classical physics, specifically the issue of blackbody radiation. This topic, which involved understanding the radiation emitted by objects, became central to Planck's career. Blackbody radiation posed a serious problem to physicists of the time, and its resolution would eventually lead to a complete overhaul of how energy, matter, and light were understood. Planck's first major breakthrough came when he applied a mathematical solution to this problem that incorporated the concept of energy quantization. Classical physics, based on the principles of Newtonian mechanics and Maxwell's electromagnetic theory, was unable to explain why a black body, heated to a high temperature, would emit radiation in a specific way. Classical theories predicted that the intensity of radiation would continue to increase infinitely as the wavelength of emitted radiation decreased, especially in the ultraviolet range, a phenomenon called the ultraviolet catastrophe. This was clearly not observed in experiments, where radiation intensity tapered off as the wavelength decreased. The inability of classical physics to explain this discrepancy led to one of the greatest theoretical challenges in physics. To solve this, Planck began his search for a new approach that would reconcile theory and experiment. He introduced the concept of quantized energy, suggesting that energy could only exist in discrete units, or quanta, rather than being continuous. This hypothesis was quite radical at the time, as it directly contradicted the established beliefs of classical physics. Classical physics viewed energy as something that could vary continuously, without restriction, but Planck's theory proposed that radiation could only be emitted or absorbed in discrete amounts, each corresponding to a specific frequency of radiation. The introduction of energy quantization solved the ultraviolet catastrophe by applying this principle to the problem of blackbody radiation. Planck derived a formula that accurately described the observed spectrum of radiation, including both the short wavelength and long wavelength regions, something classical physics could not do. Planck's radiation law, formulated in 1900, was an immediate success in matching experimental observations. However, his approach to quantizing energy was not initially accepted as a fundamental theory. Instead, it was treated as a mathematical tool, something to make the data fit better rather than a reflection of deep physical truths. Planck himself saw the introduction of discrete energy levels as a temporary measure to solve the blackbody radiation problem, not as a new fundamental principle of nature. He had no idea that his work would lay the groundwork for a new branch of physics. This reluctance to fully embrace the implications of his own work would become a theme throughout his career. Despite his hesitations, Planck's discovery marked the beginning of a seismic shift in the way physicists thought about energy, matter, and light. Planck's constant, introduced as part of his radiation law, became one of the most important constants in physics. The constant, denoted as h, describes the relationship between the energy of radiation and its frequency. This constant would later become one of the most important quantities in quantum mechanics, used in a wide range of equations and theories. Although Planck did not immediately realize it, his constant and his concept of energy quanta were the keys that would eventually unlock the entire field of quantum mechanics. As the concept of quantization gained more attention, it was taken further by other physicists, most notably Albert Einstein. In 1905, Einstein used Planck's idea of quantized energy to explain the photoelectric effect, where light shining on a metal surface causes the emission of electrons. Classical theories had failed to explain why only light of certain frequencies could cause electron emission, regardless of its intensity. Einstein proposed that light itself was quantized, existing as discrete packets of energy, which he called photons. This explanation not only supported Planck's theory but also provided experimental evidence for the validity of quantization. Einstein's work on the photoelectric effect played a crucial role in the acceptance of quantum theory, and it earned him the Nobel Prize in Physics in 1921. Einstein's contributions demonstrated the power of Planck's insight into energy quantization, showing that it applied to a wide range of phenomena, not just blackbody radiation. The photoelectric effect became one of the key pieces of evidence supporting the theory of quantization. Planck's theory was thus expanded from the realm of blackbody radiation to encompass a broader understanding of the interaction between light and matter, eventually laying the groundwork for the full development of quantum mechanics. However, the full implications of Planck's work were still not clear at this point. It would take additional breakthroughs and the work of other scientists, like Niels Bohr and Werner Heisenberg, to fully realize the impact of Planck's ideas. The next major development came with Niels Bohr's work on atomic structure. In 1913, Bohr applied the concept of energy quantization to the behavior of electrons within atoms. Bohr proposed that electrons in atoms could only occupy certain discrete energy levels. This was a direct application of Planck's ideas about energy quantization and marked a significant step in the development of quantum mechanics. Bohr's model of the atom successfully explained the discrete spectral lines observed in the emission spectrum of hydrogen, something that had puzzled scientists for years. Bohr's model, while limited in its scope, was a key development that helped cement the idea that quantization was not just an ad hoc solution to a specific problem, but a fundamental feature of the universe. Although Bohr's model was groundbreaking, it was still based on ideas that were fundamentally classical in nature. It was Planck's work that had laid the foundation for these later developments, and it was Planck's constant that played a crucial role in the mathematical formulation of the quantum theory. However, the full implications of quantum mechanics were only beginning to emerge. It was Planck's quantization of energy that triggered a whole new way of thinking about the nature of light, matter, and energy, leading to the eventual development of quantum mechanics, a theory that would forever alter our understanding of the universe. Planck's work also had far-reaching consequences in other areas of physics, particularly in statistical mechanics and thermodynamics. Statistical mechanics, which deals with the microscopic behavior of particles in large systems, was significantly advanced by Planck's insights into quantization. His work helped establish a bridge between classical thermodynamics, which deals with macroscopic properties like temperature and pressure, and the quantum theory, which deals with the behavior of individual particles. This connection between classical and quantum mechanics helped lay the groundwork for the later development of quantum statistical mechanics, which has played a crucial role in understanding phenomena like superconductivity, quantum fluids, and the behavior of atomic and subatomic particles. Despite the far-reaching consequences of his work, Planck remained hesitant to fully embrace the implications of quantum theory. His deep philosophical convictions about the nature of reality made him uncomfortable with the uncertainty and indeterminism inherent in quantum mechanics. While Planck recognized the power of quantum theory in explaining experimental results, he remained committed to the idea that the universe was governed by deterministic laws. This philosophical reluctance to accept the full implications of quantum mechanics, especially the role of uncertainty, set him apart from other key figures in the development of quantum theory. such as Heisenberg and Bohr. Although Planck's own views were more conservative, his contributions provided the foundation for the explosive growth of quantum mechanics in the 20th century. His work allowed later scientists to develop a theory that not only explained the behavior of radiation and matter at small scales, but also reshaped our understanding of the nature of reality itself. Quantum mechanics, with its focus on probability and uncertainty, fundamentally altered the way we think about the universe, revealing a world that behaves very differently from our everyday experiences. Through his search for the laws behind the laws of nature, Planck transformed the landscape of physics, paving the way for one of the most successful theories in the history of science. Max Planck's contributions were transformative. His introduction of energy quantization, encapsulated in the concept of Planck's constant, was the catalyst for the quantum revolution. His work opened the door to a new era in physics, one that would radically alter how we understand the universe. Planck's role as the father of quantum theory is solidified by the profound impact of his work, which continues to influence modern physics and our understanding of the fundamental nature of reality. His intellectual journey serves as a powerful reminder of the importance of questioning established paradigms and the power of scientific curiosity to unlock the deepest truths about the world around us. Max Planck's work revolutionized the field of physics, particularly through his introduction of quantization in energy. This groundbreaking idea emerged from his attempt to resolve one of the most perplexing problems in classical physics, the ultraviolet catastrophe. The problem arose when classical theory predicted that a black body, an idealized object that absorbs all radiation, would emit an infinite amount of energy at short wavelengths. This prediction clearly contradicted experimental observations, where the intensity of radiation decreased as the wavelength shortened. To solve this, Planck introduced the radical idea that energy could only be absorbed or emitted in discrete packets, or quanta. This was a dramatic departure from the classical view that energy was continuous. By introducing this quantization, Planck was able to derive a mathematical formula that accurately described the observed spectrum of blackbody radiation across all wavelengths, providing a resolution to the ultraviolet catastrophe. Planck's constant, h, became a fundamental quantity in quantum theory, a crucial element that underpinned the entire framework of quantum mechanics. Planck's concept of quantization was met with some resistance, both from other physicists and from Planck himself. Initially, Planck viewed this idea as a temporary mathematical tool, something to fit experimental data, rather than a true reflection of nature's laws. He was deeply influenced by classical mechanics, which adhered to the principle of determinism, and thus struggled to accept the implications of the probabilistic nature of quantum theory. Planck himself was uncomfortable with the radical departure from classical physics, especially the idea that energy levels could only take on discrete values, as this seemed incompatible with his deeply held belief in a continuous, deterministic universe. Nonetheless, the accuracy of his radiation law in explaining black body radiation left little room for skepticism about the validity of his findings. Despite his reservations, the quantization of energy marked the dawn of quantum mechanics, forever altering the trajectory of physics. The true significance of Planck's work became apparent only in the years following his discovery. Albert Einstein, in 1905, used Planck's quantization to explain the photoelectric effect, in which light striking a metal surface caused the emission of electrons. Classical physics had predicted that the intensity of light, rather than its frequency, should determine whether electrons would be emitted. However, experiments showed that only light of certain frequencies caused electrons to be emitted, regardless of its intensity. Einstein proposed that light itself was quantized, composed of discrete packets of energy, which he called photons. This explanation supported Planck's earlier theory and extended it into a new realm, that of light. Einstein's use of Planck's ideas was a crucial moment in the development of quantum mechanics and earned him the Nobel Prize in Physics in 1921. His work demonstrated that energy quantization was not just a mathematical construct for explaining blackbody radiation, but a fundamental property of nature that could be applied to light and matter alike. In the wake of Einstein's work, Niels Bohr further developed Planck's ideas by applying them to the atomic model. Bohr proposed that electrons within atoms could only occupy specific, quantized energy levels, and that they could move between these levels by emitting or absorbing discrete packets of energy. This model helped explain the discrete spectral lines observed in atomic spectra, a phenomenon that had long puzzled scientists. Bohr's model marked a significant step in the development of quantum theory, as it applied Planck's concept of energy quantization to the structure of atoms, further solidifying the idea that the microscopic world was governed by fundamentally different rules than those governing macroscopic objects. Bohr's work was one of the key developments that led to the establishment of quantum mechanics as the primary framework for understanding the behavior of matter and energy at small scales. Planck's work was not just theoretical, but also had profound implications for experimental physics. His quantization theory laid the groundwork for many of the technological advances that emerged in the 20th century. The development of quantum theory eventually led to innovations in fields such as semiconductors, lasers, and quantum computing. Technologies that rely on quantum mechanics have revolutionized industries ranging from telecommunications to medicine. For instance, the understanding of energy quantization led to the development of lasers, which rely on the emission of photons in discrete energy levels. Similarly, semiconductors, which are the backbone of modern electronics, owe their development to quantum principles. Even today, quantum mechanics continues to be at the forefront of research as scientists work to develop new technologies, such as quantum computers, that exploit the strange and counterintuitive properties of quantum systems. Planck's contributions, though formulated over a century ago, remain central to the scientific and technological advancements of the modern world. In conclusion, Max Planck's introduction of energy quantization marked a turning point in the history of physics. His work resolved the ultraviolet catastrophe, laying the foundation for the development of quantum mechanics. Though initially met with resistance, Planck's ideas were later extended by Einstein, Bohr, and others, transforming our understanding of the microscopic world. His discovery also paved the way for technological advancements that have had a profound impact on modern society. Planck's work continues to resonate in the field of physics, reminding us of the importance of challenging established ideas and pushing the boundaries of human knowledge. Max Planck's contributions to science were monumental, but perhaps his most significant was his introduction of the idea that energy is quantized. In the late 19th century, scientists were struggling to understand the behavior of radiation emitted by a black body, a theoretical object that absorbs all incoming radiation and re-emits it. Classical physics, based on laws formulated by Isaac Newton and James Clerk Maxwell, predicted that black bodies should emit infinite amounts of radiation at short wavelengths, which led to the ultraviolet catastrophe. The classical predictions didn't match experimental data, which showed a tapering off of radiation at higher frequencies, especially in the ultraviolet range. This discrepancy forced scientists to reconsider the foundations of classical physics and search for a new explanation. Planck, driven by the need to resolve this problem, approached it from a completely new angle. Instead of adhering to the classical assumption that energy could vary continuously, he proposed that energy could only be emitted or absorbed in discrete units, or quanta. This was a revolutionary idea. Planck's hypothesis was driven not by a philosophical belief in the nature of the universe, but by the need to make his mathematical model match experimental data. He introduced the concept of Planck's constant, denoted h, which linked the energy of radiation to its frequency. This formula, which became known as Planck's radiation law, successfully described the observed radiation spectrum across all wavelengths, including the ultraviolet range, thereby solving the ultraviolet catastrophe. His discovery marked the birth of quantum theory, although at the time, Planck himself viewed his idea more as a mathematical convenience than as a radical shift in understanding. Planck's work was a paradigm shift, but the implications of his discovery weren't immediately understood or accepted by the scientific community. Classical physics had been dominant for centuries, and the idea of quantized energy seemed radical. Planck himself was not fully comfortable with the philosophical implications of his own work. He continued to believe that energy should, in principle, be continuous and that the quantization of energy was just a tool to solve a specific problem. This reluctance to fully accept the meaning of his own discovery would characterize much of Planck's career. Despite this, his work was foundational for what would later become the field of quantum mechanics. His constant H became a cornerstone of the new theory, and his radiation law provided the mathematical framework that underpinned the development of quantum theory. The next major leap in the acceptance of quantization came through Albert Einstein's work on the photoelectric effect. In 1905, Einstein applied Planck's concept of quantization to explain the photoelectric effect, a phenomenon in which light shining on a metal surface causes the emission of electrons. Classical physics had predicted that the intensity of light, not its frequency, would determine the energy of emitted electrons. However, experiments showed that only light of a certain frequency could cause electron emission, regardless of the intensity. Einstein proposed that light itself was quantized and consisted of discrete packets of energy, or photons. This concept was directly inspired by Planck's earlier work on energy quantization, and it provided experimental evidence supporting Planck's theory. Einstein's work, which earned him the Nobel Prize in Physics in 1921, was a significant validation of Planck's theory of quantization. It extended the idea of quantized energy from blackbody radiation to light itself, confirming the applicability of Planck's hypothesis beyond its original context. Following Einstein, Niels Bohr extended Planck's quantization ideas to atomic theory. In 1913, Bohr developed a model of the atom in which electrons were restricted to specific quantized energy levels. This model, based on Planck's quantization of energy, successfully explained the discrete spectral lines observed in the hydrogen atom's emission spectrum. According to Bohr's model, when an electron transitions between these quantized energy levels, it emits or absorbs a quantum of energy in the form of light. This concept, built directly upon Planck's work, was crucial in explaining atomic spectra and laid the groundwork for the development of modern quantum mechanics. Bohr's model was a key milestone in understanding atomic structure and the behavior of electrons, and it demonstrated the power of Planck's theory to explain phenomena beyond blackbody radiation. Planck's work did not just influence theoretical developments, but also had profound practical consequences. The advent of quantum mechanics, catalyzed by Planck's discovery, led to technological breakthroughs that transformed the modern world. Quantum mechanics is foundational for many technologies, including semiconductors, lasers, and quantum computing. Semiconductors, which are essential to modern electronics, operate based on quantum principles. The development of lasers, which rely on the emission of photons in discrete energy levels, is another direct consequence of Planck's theory. Furthermore, quantum computers, which leverage the principles of superposition and entanglement, have the potential to revolutionize fields like cryptography, medicine, and artificial intelligence. These technologies are now integral parts of modern life, and they trace their roots back to the quantization of energy first proposed by Planck. Planck's legacy is not just about his specific scientific achievements, but also about his role in shifting the entire scientific worldview. His introduction of quantization challenged the deterministic framework of classical physics and opened the door to a new era of uncertainty and probability. The advent of quantum mechanics fundamentally altered our understanding of the universe, revealing a world where particles and energy behave in ways that are often counterintuitive and unpredictable. Planck's work set the stage for the exploration of this strange new world, which continues to yield surprises and challenges. The quantum world, governed by the principles of superposition, entanglement, and uncertainty, is radically different from the macroscopic world of classical mechanics. Planck's discovery of quantized energy provided the first hint of this new reality, and his insights continue to shape our understanding of the universe today. In conclusion, Max Planck's introduction of energy quantization marked the beginning of the quantum revolution. His work, which solved the ultraviolet catastrophe, laid the foundation for the development of quantum mechanics and opened up new possibilities for understanding the behavior of light and matter. While Planck himself was hesitant to embrace the full implications of his discoveries, his work paved the way for the breakthroughs of Einstein, Bohr, and other physicists. The legacy of Planck's work is not just in the specific theories he developed, but in the paradigm shift he initiated, one that continues to shape modern physics and technology. Planck's contributions remain foundational to the scientific advances that have transformed the 20th and 21st centuries, and his work serves as a reminder of the power of curiosity and intellectual courage in advancing human knowledge. Max Planck's revolutionary contributions to the field of physics marked a significant turning point in the history of science. His discovery of energy quantization, driven by his attempt to resolve the ultraviolet catastrophe, introduced the first steps towards what would later become quantum mechanics. The ultraviolet catastrophe was a problem that arose when classical physics failed to explain the behavior of blackbody radiation, which is the electromagnetic radiation emitted by an object that absorbs all incident radiation. Classical theory predicted that a blackbody would emit infinite energy at shorter wavelengths, which contradicted experimental observations. This paradox, known as the ultraviolet catastrophe, was a central issue in the physics community and prompted Planck to seek a new approach to the problem. Planck's solution came in the form of his groundbreaking idea that energy is not continuous but comes in discrete quantities, or quanta. Instead of assuming energy could take any value, as classical physics did, Planck proposed that energy could only be absorbed or emitted in fixed, quantized amounts. This was a radical departure from the classical view, which treated energy as a smooth, continuous quantity. By introducing the concept of quanta, Planck was able to derive a formula, known as Planck's radiation law, that perfectly matched experimental data on blackbody radiation. His formula resolved the ultraviolet catastrophe by accurately describing how radiation behaves at all wavelengths, providing a mathematical foundation that classical physics could not offer. However, Planck himself did not initially recognize the profound implications of his discovery. His primary goal was to find a mathematical solution to a specific problem, not to revolutionize our understanding of the universe. At first, Planck viewed quantization as a mathematical tool, a temporary fix to fit the data rather than a fundamental feature of nature. This reluctance to embrace the broader consequences of his work was characteristic of Planck's thinking. He continued to believe in the idea of a deterministic, continuous universe, which made it difficult for him to accept the radical nature of quantum theory. Nonetheless, his work was groundbreaking, and the constant he introduced, Planck's constant, became one of the most important quantities in modern physics. The implications of Planck's discovery became more apparent as others, like Albert Einstein, extended his ideas. In 1905, Einstein applied Planck's concept of energy quantization to explain the photoelectric effect, where light striking a metal surface causes the emission of electrons. Classical physics had predicted that the intensity of light, rather than its frequency, should determine whether electrons are emitted. However, Experiments showed that only light of certain frequencies could cause electron emission, regardless of its intensity. Einstein proposed that light itself was quantized, made up of discrete packets of energy, or photons. This idea, directly inspired by Planck's work, confirmed the validity of energy quantization and extended it to light. Einstein's explanation earned him the Nobel Prize in Physics in 1921 and provided strong experimental support for Planck's theory. Niels Bohr further expanded on Planck's work by applying quantization to the behavior of electrons in atoms. In 1913, Bohr proposed that electrons could only occupy specific, quantized energy levels within an atom, and that the emission or absorption of energy occurred when an electron moved between these levels. This model successfully explained the discrete spectral lines observed in hydrogen's emission spectrum. Bohr's work, which built directly upon Planck's quantization of energy, was crucial in developing the early framework of quantum mechanics. It demonstrated that the principles of quantization could explain not only radiation from black bodies, but also the behavior of atoms, marking a significant step in the development of atomic theory. Planck's contributions were not limited to theoretical advancements. His ideas also had profound practical implications. The development of quantum mechanics, catalyzed by his work, paved the way for a number of groundbreaking technologies. For instance, semiconductors, which are the foundation of modern electronics, rely on quantum principles to explain the behavior of materials at small scales. Lasers, which depend on the principles of photon emission and absorption, were also made possible by Planck's quantization theory. More recently, quantum computing, which leverages the strange properties of quantum mechanics, has the potential to revolutionize fields such as cryptography, artificial intelligence, and medicine. Planck's work, while theoretical at first, has led to technologies that are now ubiquitous in modern life. While Planck's ideas were central to the development of quantum mechanics, he himself was hesitant to fully embrace the full philosophical implications of the theory. He struggled with the idea of uncertainty and probability in quantum mechanics, which contrasted sharply with his belief in a deterministic universe. Quantum mechanics, particularly the work of Werner Heisenberg on uncertainty, suggested that certain quantities, such as position and momentum, cannot be simultaneously known with absolute precision. Planck, however, remained steadfast in his belief that the universe operated according to precise, deterministic laws. Despite this, he continued to support the growing field of quantum mechanics, recognizing that the theory was not only successful in explaining experimental data, but also provided a deeper, more accurate description of the physical world. Planck's intellectual journey, marked by both his skepticism and his acceptance of quantum theory, reflects the broader challenges faced by many scientists during the early days of quantum mechanics. In conclusion, Max Planck's introduction of energy quantization was the cornerstone of modern quantum theory. His work provided a solution to the ultraviolet catastrophe and set the stage for the revolutionary developments that followed, including Einstein's work on the photoelectric effect, Bohr's model of the atom, and the eventual development of quantum mechanics. Planck's constant became a fundamental constant in physics, underpinning many of the equations and principles that govern the behavior of energy, matter, and light. His discoveries also paved the way for groundbreaking technologies, from semiconductors to quantum computers, that continue to shape modern society. Despite his initial reluctance to fully accept the implications of his work, Planck's legacy as the father of quantum theory is secure. His intellectual courage and perseverance in the face of uncertainty laid the foundation for the next century of scientific discovery, and his work continues to inspire physicists and researchers to this day. Max Planck's work fundamentally reshaped the landscape of physics and paved the way for the quantum revolution. His quest began with the effort to understand the nature of blackbody radiation, a problem that had been perplexing scientists for decades. A blackbody, an idealized object that absorbs and emits all radiation perfectly, was thought to emit radiation in a specific pattern as its temperature increased. However, classical physics, particularly the laws of thermodynamics and electromagnetism, predicted that this radiation would increase indefinitely as the wavelength shortened, leading to a paradox known as the ultraviolet catastrophe. The theoretical models based on classical physics did not match experimental observations, which showed that the intensity of radiation decreased at shorter wavelengths. This inconsistency left a significant gap in understanding and was one of the major problems that Max Planck sought to solve. In 1900, Planck introduced a radical new idea to solve this problem: energy is quantized. Rather than considering energy as a continuous flow, Planck proposed that energy could only be absorbed or emitted in discrete amounts, which he called quanta. This was a revolutionary departure from the classical view, which assumed energy could take on any value. Planck's hypothesis was formulated as a mathematical necessity to reconcile the discrepancy between classical theory and experimental data. He derived a formula known as Planck's radiation law, which accurately described the spectrum of radiation emitted by a black body at different temperatures. This law perfectly matched experimental observations, resolving the ultraviolet catastrophe. The constant introduced in his equation, now known as Planck's constant, became a cornerstone of quantum mechanics and is fundamental to the field. Although Planck's radiation law successfully explained blackbody radiation, he did not immediately recognize the full implications of his discovery. Initially, he saw the idea of quantized energy as a temporary mathematical tool rather than a profound insight into the nature of reality. He continued to believe in a classical, deterministic universe where energy should be continuous, and he did not fully embrace the concept of quantization as a fundamental property of nature. Nonetheless, his work marked the beginning of a paradigm shift in physics. The idea of quantization would soon become one of the most important concepts in the emerging field of quantum mechanics, a concept that would challenge the very fabric of classical physics. The true significance of Planck's work began to unfold with the contributions of other scientists. In 1905, Albert Einstein used Planck's concept of energy quantization to explain the photoelectric effect. The photoelectric effect involves light striking a metal surface and causing the emission of electrons. Classical physics had predicted that the intensity of light, rather than its frequency, should determine the energy of emitted electrons. However, experiments showed that only light of certain frequencies could cause electron emission, regardless of its intensity. Einstein proposed that light itself is quantized, existing as discrete packets of energy called photons. This extension of Planck's quantization theory not only validated Planck's work, but also demonstrated that quantization applied to light as well as matter. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921 and solidified the concept of quantized energy as a fundamental principle of the universe. The next significant leap came with Niels Bohr's model of the atom in 1913. Bohr applied the idea of quantized energy levels to the structure of atoms. He proposed that electrons in atoms could only occupy specific quantized energy levels, and that radiation was emitted or absorbed when electrons transitioned between these levels. Bohr's model successfully explained the discrete spectral lines observed in hydrogen's emission spectrum, a phenomenon that had eluded classical physics. This model was a critical step in the development of quantum mechanics and demonstrated the far-reaching implications of Planck's work. Bohr's success in applying quantization to atomic structure showed that the principles of quantization were not just confined to the behavior of radiation, but were fundamental to the behavior of matter itself. Planck's theory of quantization also had important implications for other areas of physics, particularly in statistical mechanics and thermodynamics. Statistical mechanics, which seeks to explain macroscopic properties like temperature and pressure by considering the microscopic behavior of particles was significantly advanced by Planck's insights. Planck's work on the distribution of energy and systems of particles helped bridge the gap between classical thermodynamics, which was based on macroscopic observations, and quantum theory, which focused on the microscopic scale. This bridge would be crucial in developing quantum statistical mechanics, which is essential for understanding phenomena like superconductivity and quantum fluids. While Planck's work laid the foundation for much of modern physics, he remained cautious about fully accepting the radical nature of quantum mechanics. Planck's own philosophical stance was rooted in classical ideals, and he struggled with the implications of quantum mechanics, particularly the inherent uncertainty and probabilistic nature of the theory. In contrast to the deterministic view of classical physics, quantum mechanics, as developed by Heisenberg and others, introduced an element of unpredictability. Planck, however, continued to support the development of quantum theory because it provided the best explanation of experimental data. Despite his reservations, he recognized that the theory's success in explaining the behavior of the atomic and subatomic world was undeniable. Planck's work also had profound practical consequences. His contributions to the development of quantum theory led to technological breakthroughs that transformed the modern world. Semiconductors, the basis for modern electronics, rely on quantum mechanics to explain the behavior of materials at the microscopic level. Lasers, which depend on the principles of photon emission and absorption, also trace their origins to Planck's ideas about quantization. More recently, quantum computing has emerged as one of the most promising technological advancements, with the potential to revolutionize fields like cryptography and artificial intelligence. These technologies, though still developing, owe much of their foundation to Planck's groundbreaking work in the early 20th century. In conclusion, Max Planck's discovery of energy quantization was the cornerstone of quantum mechanics. His resolution of the ultraviolet catastrophe laid the groundwork for the development of modern physics, influencing not only theoretical developments, but also practical technologies that have changed the world. Although Planck himself was reluctant to embrace the full implications of his work, his contributions set the stage for the later breakthroughs by Einstein, Bohr, and others. Planck's work continues to be a driving force in the advancement of scientific knowledge, reminding us of the importance of questioning established ideas and the power of intellectual curiosity to unlock the deepest truths about the universe.